the last thing we're going to talk about in this chapter is density. And density is basically the sort of property of matter that determines, for example, whether or not something will sink or float. And if something is more dense than, say, liquid water, it will sink. If something is less dense than liquid water, it will float, which is what we see here. We got some objects floating, and we clearly have some objects that are sinking. So density is basically the mass of a substance to its volume. It has a formula of D is equal to M divided by V. And we should think of this as a formula, which it is, and it is a formula that you do need to know. And we do have to rearrange it. So if we want to solve for volume, volume would be mass divided by density. We would basically multiply the volume to both sides, divide by the density to both sides is essentially what we did there. Now, if we want to solve for mass, mass would be the volume times the density. Sometimes people will remember this by the DMV triangle. Everybody loves the DMV. Density is mass over volume. Volume is mass over density. And mass is volume times density. So in terms of units for density, typically for solids and liquids, they have units of grams per milliliter or grams per cubic centimeter. Remember that a milliliter is equal to a cubic centimeter. It is a one-to-one relationship. We really don't come across it too much in this class, but when you deal with gases, the units of density for gases are typically grams per liter. I would say for us, pretty much these are going to be the two units that you will mostly see in terms of density. And really in terms of the volume, you really can get the volume a couple ways. You could get it by simply just taking a volume reading. So you put some liquid into a cylinder and take an actual correct volume reading. Remember that cubic centimeters is found by taking something like the length times the width times the height, where you measure them all in centimeters. And again, when you multiply them together, you get a volume like a cubic centimeter. So that's a very common way that you can find the volume of a solid object, like a cube or something like that, is to take those three sort of measurements. So the higher the density, typically particles are really packed together a lot closer. The lower the density, usually they're also kind of further apart from each other. One kind of common exception, for example, where that really doesn't hold true is something that we see probably most days is ice. Ice is the solid version of water. And when we put ice in our drink, it ends up where? Top, right? It ends up floating on top. And that's because when water comes together, it is actually held together by what's referred to as hydrogen bonding. And when they come together in the solid state, what actually happens is they actually can't get super close to each other. And that's very unusual for a substance. Most of the time when they get into the solid state, a substance pretty much can pack right into one another and they get really close to each other. But because of the way they bond, when water kind of gets close to each other in the solid state, they really can't get super close. And if you think about the density equation, which is our mass over volume, what happens is it creates a big open volume between the different water molecules, and it makes this number larger, which ends up making the density of ice smaller, right? If you divide by a larger number, you end up with a smaller number for the density. And that's a very unusual sort of characteristic of water. Most things in their solid state much, much more dense than in their liquid state. So as I mentioned before, these are our common units of density, our grams per cubic centimeter, our grams per milliliter, and again, for gases, grams per liter. Here are some of the density values of some common substances. I would say that water's density, and that's liquid water, by the way, and density does change with temperature. The liquid water density if you ever need it, 1 gram per milliliter is typically the value that you would use for density. So sometimes in problems, you'll come across a situation where like, I feel like I need the density of water, and 1 gram per milliliter is typically the value that you could use. It does change, as we just talked about. Ice is a lot less dense, as you can see there, 0.92 for ice, which is why it actually will float in water, right? It's actually less dense than 1 as well. So, any of these guys are going to sink, right? And obviously, these guys here are going to float, for example, in water because it is less dense. Also, why, for example, if I took, say, a couple of soda cans, yeah, like a Diet Coke and a regular Coke, and I put it into a big sink of water, what will happen to the Coke cans? Will they both sink? Will they both float? Will they do one of each? Yeah, so if you put it in there, the Diet Coke will actually float. The regular Coke there will sink. The reason for that is what's in regular Coke? Sugar, right? And in Diet Coke, it's artificial sweetener. So with all that sugar, it's actually more dense, causes the Coke can to actually sink. Good party trick in case you need one. Guess the Super Bowl was yesterday, but you never know. Next family gathering, you could do those things. All right, so let's talk a little about another common way that we actually do get the volume of a substance. So as I mentioned before, we can get the volume by simply taking a volume reading. We could grab a ruler, do some length measurements. The other very common way that we get the volume of an object is by what's referred to as volume by displacement. And really, volume by displacement is this idea that if you take a container, for example, like a graduated cylinder, and you fill it up with some type of liquid like water, and you would have an initial volume reading when you do that. And if you take a solid object, like a piece of metal, and you drop it into the graduated cylinder, what's going to happen to the water level in there is, will it go down, up, stay the same? Should go up, right? And with their little metal piece in there, and you'll have a final volume reading on the graduated cylinder. So if you take the difference between the initial, that's a long drawing, and the final markings there, that volume difference is the volume of the object. And that would be found by taking the final volume minus the initial volume. So that's a very common way and very easy way that you can basically find the volume of a solid object. You basically just drop it in there, take the difference between the volume, final minus initial, and that will get you your actual volume of that particular object, which is what we kind of see in this example here. Before they put the zinc in, it had a volume of what we got there, 35.5. After they weighed out a certain amount of zinc and they put it in, the volume of water got displaced by that much volume and ended up 45.0 milliliters. So our mass over volume here, we do want to look at significant figures. So when we subtract this, we're actually looking at decimal places here, right? So that would get us our 9.5, which should be 1 decimal place based on the subtraction. But in terms of significant figures, it has, as you can see there, 2 significant figures, right? And that's important because the last thing that we would do here is the division part, where we take the mass divided by that volume, which means we're taking 4 significant figures divided by 2, which means our answer should end up with 2 significant figures. So a lot of times when you do volume by displacement, you're calculating something like density. A lot of times these significant figures at the end of the calculation is actually based on the subtraction that you do. But you got to remember, since we're subtracting, we're actually looking at decimal places first, which will give you the proper answer to the proper number of significant figures. And then you got to transition from decimal places to significant figures when you do the division part of the density calculation. Question on that? All right, so what is the density here of 48 gram sample that started with 25 milliliters of water and then went to 33 afterwards? So why don't you calculate it up? Got little pictures there to look at. It's pretty good. So we'll start with our density equation, which is mass over volume. We obviously have the mass already given to us here, which is our 48.0 grams. We have our initial volume here of our water in the graduated cylinder. We're going to put that solid in there, and this is going to be our final volume. Once again, if we take the difference there, and I could draw straight lines, the difference there between those two, that's going to give us the volume of the object that went for a swim. So we do want to find the volume that way. So the volume of the object here would be our final volume, which is 33.0 milliliters minus our initial of 25 milliliters. That's going to give me 8.0 milliliters. I do need the zero. Why? Because we should be looking at decimal places, right? In this case, there's one decimal place on both of them, which means even though my calculator spit me an 8 out, it actually needs 8.0 to have the proper number of significant figures in this case, right? Our decimal places to gives us proper number of significant figures. That's really important for the last part of the calculation where we take the density, right? And now we take our mass and we divide it by our 8.0 milliliters. And when we do that, we got 48 divided by 8, going to give us 6. And the proper significant figures should be how many in this case? It should be 2 because we do have 3 here and we're dividing here at the end. And this is why it's important that we did put the 0. This should be there because that's technically 2 significant figures, which means we do have to add a 0 here. Now, in terms of the units, do they cancel? They don't. They should still be there at the end. So it should be 6 grams per milliliter. The number always stays with the grams part, and it's always 1 milliliter or 1 cubic centimeter. Any questions on that? So again, it's important to, and sometimes people get a little confused as they're doing it. You got to first look at decimal places here to get the proper decimal places. Then you got to switch gears to significant figures as to how many you got going on there. So again, if you forget the 0 at any of those locations, you will get the wrong answer in terms of significant figures right at the end there. Any questions on that one there? Okay. Hey, and they agree. That's good. All right. So let's try this one. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample of this liquid? So we want to think about our density equation, which is density is equal to mass over volume. And we are given the density in this case, which is 1.32 grams per milliliter. We also have the mass given to us, which is 14.7 grams. So if you're not sure, obviously you have the mass, you have the density. So clearly volume seems like a pretty good thing to solve for. And you could solve for volume here. And once again, volume would be mass divided by density. Again, if you wanted to do the DMV triangle there, we have volume is mass divided by density, right? Now, let's just say perhaps can't remember the formula, maybe rearranging the formula is not your thing. This is again where, as I might have said last time, dimensional analysis can also be very helpful to figure out the sort of math part of it or the rearranging part. So because we do have like a density value that has 2 units, that's pretty much like a conversion factor. And we could use the density value like a conversion factor, which means we could flip this around and do milliliters on top and 1.32 grams. Now, the benefit of doing it this way is pretty much we could take a dimensional analysis approach without even really have to thinking about any of these equations and just go, I want to get rid of grams and I want to end up with milliliters, right? So we could just think about our opposites approach. And we would start with the grams, which is the 1 single unit, which is typically what you start with, right? If you don't have 2 units. And again, at this point, I don't have to worry about rearranging an equation. I just go back to the dimensional analysis approach, which means I should put grams on top or bottom here to do it correctly. Doesn't need to go on the bottom, which would mean I would want to use the conversion factor of density in this fashion. And now without even having to think about the density equation or really rearrange the density equation, I just rearrange the density equation and solve for volume in this case without having to actually do it. So again, this is an added benefit of setting things up with dimensional analysis and just thinking about, what units you need to get rid of, what units you want to be left with. And it also sets you up again. You don't even have to really think about it too hard because we know, again, everything on top gets multiplied, right? And everything on the bottom gets divided. So now I know I'm going to do the right math here, which is essentially 14.7 divided by 1.32, which is pretty much what that says, right? Mass divided by density. So again, setting it up like this allows you to kind of do the formula without having to do the formula, just kind of keeping things opposite of each other. By the way, it looks like on my calculator, I got a lot of numbers there. 11.13636364 milliliters. In terms of significant figures, we have to look at all the numbers here, right? So they're all important. That's got 3. This one has got 3, which means we should end up at 3 here at 11.1 milliliters. So absolutely, you could rearrange the equation. You could plug the numbers in and get the answer. But once again, if you're unsure about how to do that properly or not super confident, taking a more dimensional analysis approach and just setting up the units works the math out for you without you having to sort of rearrange it. So sometimes it's, very, very helpful. Also, like the previous example or previous example, we're doing how many days. I can't tell you how many people, when we would do a problem like that, would be multiplying by the 60 and 24 instead of being dividing what you need. So again, it just keeps everything where it should be. Any questions on that there? All right. Maybe one last one here before we wrap it up for this chapter here. John took 2 teaspoons of cough syrup for a cough. Syrup has a density of 1.2 grams per milliliter, and there is 5 milliliters in 1 teaspoon. What is the... Okay, so let's take a look. Once again, we're obviously dealing with some density, so we could look at the equation. And also a good idea is to pull out information from the problem. Sometimes it does give you an idea as to where you should maybe try to go to. 2 teaspoons is actually a volume, right? So 2 teaspoons. We also have the density of 1.2 grams per milliliter. And we also have a conversion factor or an equality of 5 milliliters is 1 teaspoon, which we could use obviously to convert our teaspoons into milliliters, right? Which is a useful volume there when we're dealing with density. So in this particular case, we do have the density and we do have the volume. So we would be looking for mass. And if you rearrange this equation, mass would be volume times density. Again, if you use that triangle there, mass would be density times volume. So again, I'm going to take more of a dimensional analysis approach, so I don't really have to worry about maybe rearranging the equation incorrectly or something like that. So I'm just going to think about it like a dimensional analysis conversion factor type problem, which means, as we've done before, this volume here and this volume here are different. So we do have to put them into the same unit. So that's what I'm going to do first. So I'm going to take my 2 teaspoons. And in this case, I want teaspoons to cancel. So I do need to go opposite, right? Which would put it on the bottom. And up on top should be my 5 milliliters, right? Teaspoons here should cancel. And that's going to give me 10 milliliters. What kind of significant figures should I be having at this point? I should have 2, right? So I should look at this, which is 2. Do I need to look at this? I do, right? It's a conversion from metric to that, which is also 2. We would look at the 5.0, which means technically we need 2 here, which means I maybe should lay me up a decimal there, right? If I want to kind of clean it up right now. Now that I have my volume in the units I want, I know I want to get rid of the volume here, right? And I want to end up with grams. So I could use the density once again as a conversion factor where I could flip it around and do a milliliter up on top, 1.2 grams. So here, without even have to worry about the equation, I just need to do opposites, right? So I should use conversion factor on the left or right in this case in terms of the density. The one on the left puts the milliliters in the opposite location. So once again, setting it up here with dimensional analysis, I didn't even have to bother with the rearranging of the equation here. And now I am actually doing that calculation. Milliliters will cancel. We're going to multiply what's on top. We really have nothing on the bottom to divide by since it's really 1. And we will multiply that, and that will get me 10 times 1.2. going to give me 12 grams, right? And again, I just pretty much did the rearranging of the density equation without even using the density equation and thinking of it more just as a conversion factor. A lot of formulas in chemistry, you pretty much can do that move without having to remember the equation or sort of rearrange the equation. Just think about units you don't want and units you want to end up with and use things as like conversion factors. Significant figures. All right, this has 2, and this one we do need to look at, which has 3, which means we should end up with 2 in this case here, which would be 12 grams. Question on density. Yeah. So I would highly recommend kind of setting up with dimensional analysis. Again, you can just plug and chug into the equation, but I've seen that equation rearranged incorrectly a lot of times. People will do it. So this is just another sort of safeguard that hopefully will allow you to set things up correctly and do the math correctly. Any questions on that there? All right, that is density. That is specific gravity. And it has an X on it, so clearly we're not going to do it because somebody put an X on it, so we're just going to not worry about that.